welcome back everybody to our webinar series for another interesting webinar. So today it is my pleasure to introduce to you Julia Bazińska. Julia is a senior research engineer at Lakera, where her interests span NLP, AI security, and performance optimization of ML systems. At Lakera, she works on a tool called Lakera Guard, which develops secure AI applications and agents to protect them from attacks like prompt injections, data leaks, and similar attack vectors. And today, Julia is going to tell us about her paper called Breaking Agent Backbones, Evaluating the Security of Backbone LLMs in AI Agents, which I believe you just presented at ICLR, correct?
Yes, that's correct.
Correct. Well done for getting into ICLR with the paper. Okay, so without further ado, the mic is yours, Julia. Thanks very much.
Okay, let's go. So number one, thanks everyone for coming. And yeah, I hope you'll find this interesting. Yeah, so we already had a bit of an introduction, but first I wanted to ask, how many people here know Gandalf? Okay, I can't. Okay, I'm getting thumbs up. Amazing. Thank you for being interactive. Yes, so in Lakera we developed Gandalf. I think it will be now 3 years ago. And this is something that kind of made us a bit well known, that also allowed us to have a lot of prompt injection related data. And because of this, we built like a defense product. And we also do like red teaming services for large language models. So just so you know who you're gonna be talking to. But I think the first thing that I wanted to talk about is what's actually the difference between AI safety and AI security. So I know that this group is called AI Safety Poland, and I will be talking about AI security. So why? And this makes me actually very happy that I'm not doing this presentation in Polish, because in Polish there is no it's the same word for both. But English is one of the few words where you do have two different words like this. And yeah, what's the difference? Let's talk about a bike. A bike is unsafe, and that would mean that for example, maybe the brakes don't work, or some screws are loose, and you're going to hurt yourself when you use this bike. On the other hand, your bike can be also insecure, and that would mean something completely different. That would mean that someone can steal your bike easily. So these are like slightly different things. If we think about this in the context of like LLM-based applications, the question I would ask is like, can a user be harmed versus can the system itself be harmed? And how does that show in AI-based applications? So just a note here first is that throughout this presentation, I will be talking about like LLM security, and this is not about LLMs existing in a vacuum, about their like net properties, but rather their properties when they exist as a part of a system. This is like a bit of a subtlety, but I just wanted to make it explicit. So yeah, there's a bunch of different things, and this is kind of my view on where I would assign them, but I'm happy to discuss this. I feel like you can take many different perspectives on the same issues and see them more as safety issues or security issues. So if we talk about producing harmful content, safety, if you look at it from the safety perspective, it's about how easy it is to make the model produce some harmful content. If you look at this from the security perspective, you're rather asking how easy it is for my user to be exposed to harmful content. So it's not only about what the model itself is going to produce, but also maybe what other guardrails were employed and things like this. So this is slightly wider and more in context. But I wanted to also like take a bit of a step back and share share the sort of perspective that I got on the field of AI security while working over the last 3 years in this field. So before we had this whole like ChatGPT LLM boom sort of a thing, we were using traditional software, and we're still using it now quite a lot, and we're using it not because it's 100% secure. We're using it because the benefits outweigh the risks. And then ChatGPT happened, and suddenly the potential attack surface increased, and people started building these very often chatbot applications. And this is something that we've seen a lot working with the industry, that we had these companies building chatbots, and their main point was to have a human in the loop. So the deliverable is either a conversation, some information that the agent is going to give, maybe some advice, maybe it's like a talk to your data sort of a setup. So it does have some tools, but the final deliverable for a long time was something that a human would use. This has changed. This has changed in the last year. So these issues caused by chatbots were, this is something that we used to call internally in the company screenshot attacks, because usually like you can have data leakage, and that's like a main issue, but the thing that we've seen happen the most was reputational damage. So someone makes the model say some bad things, takes a screenshot, and it makes a rounds on the internet, and the company loses credibility. So while this is not nice, it's still, let's say, not as bad as it has become recently, because recently the AI-based systems have gained more capabilities. There's more modalities, but mainly we have tools, we have MCP servers, and agents actually now get to interact with the virtual world properly. So the point of running them is not to give some deliverable to the human. We know we're at the stage where the agent actually does something, and it's about the thing that it does and not about the thing that it delivers to the human. And that opens up many more issues. And these are slides that I've been showing for a while, and every time I show this presentation, I sit down and I update this slide. And I think the most recent event here is happened 2 weeks ago, and there was a company that admitted that through a use of an agent to like manage their infrastructure, they lost all of their data. The agent deleted all the machine volumes with the databases, and then it proceeded to delete all the backups. So here, like the blast radius of a bad action is just much larger than it used to be, when we're just, maybe it would be something that hurts a human's eyes when they read it, but that's it. So this kind of brings me to the work that I'm here to present, and that's the paper that we presented at ICLR a few weeks ago, and we wanted to focus specifically on how the choice of a large language model affects the security of a given agent. And I want to make you understand where we're coming from with this. So this is an example deep research agent. This is just kind of like a workflow that a typical agent would execute. So kind of produces a plan on what it has to research, gathers the data in some iterative loop, creates a report, and a human reads the report, right? So this is still like a pretty basic example. And now if we want to evaluate the robustness of the system, you need to inject the potential malicious data into the data that the agent consumes, be it either the user inputs or the web search results. And this then means that you have to execute the full agentic workflow in order to know whether the attack was successful. And well, there are some issues connected to this. So number one, this tends to be kind of pricey, and well, you don't want to like have to cut costs on security, right? This is slow, and I think what's the biggest issue actually is the fact that you need to like set up a full environment. You need to set up a full sandbox environment with the fully mocked data in which you can safely execute your agent. And this gives you an understanding of like an end-to-end robustness of your system. But what we proposed in the paper is to do the so-called threat snapshot approach to things. So we take the full workflow, we chop it up into pieces, and then each of these pieces becomes a single threat snapshot. And this threat snapshot contains all the information that you need to execute the next agentic step. So what is the agent? What is it doing? What's the full context that's passed to the LLM? What's the chat history? What's some like memories, documents, whatever. So all of it is there. And there's also the threat description. And the threat description has the attack objective, the attack vector, and how do we measure whether an attack is successful. And this allows us to treat agents as completely stateless. So we have everything that's needed to execute a single step. And now if we take a look at what it is like in the example, you have in a completely benign step, well, it's just the dataset results, and we single out one of the steps of the workflow, produce the report. Cool. But in the case when we want to evaluate for robustness or resilience against attacks, you put in the attack into the search results, and you execute just the report creation step. So you assume that the attack has made it that far, and the question you're asking is, will it go one step further and cause more harm? And this has a few nice properties. So one, that's significantly cheaper, and moreover, it's simple to run because we don't need to execute any tools. We just need to have the mock data that the LLM will produce, and that's it. There's no sandboxes, there's no suffering. And that also gives us insights that are directly actionable. So you know exactly what's the attack resilience of each specific step in the workflow. And this, of course, comes with a caveat that we know the vulnerability of each component of the system, but we don't know, but we can only use that to estimate the vulnerability of the full system, and we don't know directly the vulnerability of the whole system. And this is why I think that the bitter truth here is that if you want to like deploy AI agents in truly mission critical situations, you do need to do both. You do need to do end-to-end evaluations and threat snapshot evaluations. And like for the people here who have a software engineering background, like these, I think of the end-to-end evaluations as integration tests, and the threat snapshots are basically unit tests. And in software engineering, we do both. And we did some work on the end-to-end eval side, and there is some data that we published together with NVIDIA on this, but I'm here to talk to you about what we did with Gandalf regarding this. And for the people who don't know Gandalf it's a game where the setup is quite simple. The LLM is told the password, and you're supposed to convince the LLM to reveal that password. And that's very, very easy in the beginning, but then more and more defenses are added, and that makes it harder and harder. However, this is not necessarily a very realistic scenario. So we used this concept of threat snapshots to build 10 different applications, then 10 different like states of them that span across different contexts, different attack vectors, different difficulty levels, and also different classes, like categories of risks that show in these threat snapshots. So we built this and we ran this challenge. I mean, it's still running, but at the time of the writing of the paper, we had more or less 200,000 attacks. And then that allowed us to just like select really the creme de la creme of attacks. So we selected the highest quality attacks that generalize the best. And that allowed us to develop a vulnerability score for large language models. And because this is not necessarily as expensive as it would be if we were evaluating an end-to-end system, we managed to evaluate more than 30 different LLMs. And I want to share with you a few insights from this because I think it's genuinely interesting. So I expected cloud models to do quite well. Just a remark: these are results from September, so a few more models came out, and I can share these results as well. But still, it remains true that cloud models are simply the most secure. But what was also surprising was that the grok models were also doing surprisingly well. The first time we saw this, we actually thought maybe we made a mistake, but no, actually, grok models, while they're known to be prone to produce harmful content, they're actually quite good at resisting more like security-based attacks. So kind of manipulation attempts, which is quite interesting because out of all these 10 challenges, only one of them had anything that was like related to like actually like objectively harmful content. The others were like calling bad tools and things like this. And another thing that stands out here is how open source models place in this ranking. So the striped bars are open weights models here, and you can clearly see that, well, they are kind of one level below. However, what has to be remembered here is that if it's an open weights model, I'm just evaluating the model itself, right? That's it. If it's a closed source model, it's actually not just a model, it's a full system. And I can tell you that when we were querying the Anthropic API, for sure we were flagged somehow, and at some point it took the API like 1 minute to reply to a single request because they are doing additional scans on top of the answer of the model. And another thing that's a pretty interesting takeaway, I think, is that if you look at different categories of risks and different ways LLMs fail, the performance of a specific LLM can vary quite a bit from category to category. So if we look at can you see my cursor? Oh, yes, I think you can. So if we look at the second column, which is what we call the direct context extraction, I don't want to spend time walking you through these categories, but this is basically like leaking information about the system. And here we look at grok, and grok is quite resilient. Cool, that's great. So if you're concerned about this, maybe a grok model is a good choice. However, if we look at DIO, which is what we call direct input override, meaning that you aim to make the user instructions override the system instructions. Here, grok is not nearly as good. Like it's actually significantly worse than other LLMs that were performing similarly to it in the DC category. So this just shows that like there isn't necessarily just like one best LLM, but you do need to evaluate it in a specific context, because depending on the specific context and the specific risks, the performance can change quite a lot. And something that I found really quite interesting is that we didn't find evidence that larger models are always more secure. So I was going into this thinking that larger models, of course, more capability would mean more security, but that doesn't look like that's the case. So yeah, you can see here that like within the same model family, if you compare them, then it's not, there are no clear trends, unless we're talking about reasoning. So if we look at the larger models, if we look at, well, just not the tiny models, enabling reasoning makes them more secure. And the only outliers here are GPT-5 Nano and Gemini 2.5 Flashlight, and it's the only two lines that go up. And these are really tiny models. Of course, we don't know how tiny they are, but it just seems that if you allow them to reason, they somehow become more gullible. And the last takeaway here is that security and quality are correlated to some level. So the x-axis here is the artificial analysis aggregated score, and you can see that the models become less vulnerable if they score better on the benchmark. However, there is still quite a few outliers on both sides of the line. So there are models that are high performers, but they're not secure, and there's also models that are really secure, but they don't necessarily perform very well. Yeah, so just a few perspectives for the future here, and that's, so we developed this B3 benchmark, but the reality here is that, well, the models keep evolving, and we went through the full effort of like crowdsourcing this data, but ideally we would have fully automated ways to produce attacks like this, and that would also kind of allow us to have a bit of a fairer score. Like, I do think that the score that we produced is quite fair, but it's, for example, not fair if you assume that maybe some of the providers actually will train on this data. And that will also allow us to scale up the full experiment and just have more and more categories. And as I said, this work really like isolates the vulnerabilities that stem from LLM training and just how LLMs behave, but they always behave within a system. And there is much more that can be done here. So you can do things like static analysis of agentic workflows, which are definitely like closer to traditional cybersecurity. You can analyze the tools that the agents will be calling and things like this. And as I also said, like these kind of end-to-end evaluations are also very important. So yeah, what I want to say is that you kind of need to go all in if you want to like build things that are secure. And that's what happens in traditional software, and that's what has to happen in AI as well. And that's it. Thank you very much for listening.
Okay, thanks very much, Julia. Please join me, everybody, in thanking Julia for her interesting presentation with reactions. How do I react? There we go. Okay, cool.